Welcome back to the Deep Dive. We're here again to unpack some fascinating research, cutting through the noise for you. And today, we're looking at something really intriguing in AI. It's this kind of David versus Goliath situation. These huge large language models versus, well, a surprisingly tiny competitor. We're digging into a technical paper introducing the Tiny Recursive Model, TRM for short. And honestly, this thing feels like it's almost trolling the giants. We're talking state-of-the-art results on really tough reasoning tasks like Sudoku Extreme, even the ARC-AGI benchmark. All with, get this, fewer than 10 million parameters. It's minuscule. So our mission today is pretty clear. How on earth did this tiny model, through sheer architectural simplicity, manage this? And what theoretical fixes did it make that, well, its predecessor and even the massive LLMs got wrong?
It really is a fantastic case study, isn't it? Efficiency versus just throwing compute at the problem. And you nailed the core issue right away, this LM paradox. I mean, they're incredible generalists, right? They can write poetry, code, whatever. But throw a hard puzzle at them, something needing strict step-by-step logic, they often fall apart.
Why is that, though? Is it just the scale?
It's fundamental to how they work that autoregressive generation. They predict one word or token then the next based on the previous ones. If step one of their reasoning is even slightly off, the whole chain can just go completely wrong.
Ah, right.
Yeah, and researchers have tried workarounds, things like chain of thought prompting or really expensive methods like test time compute where the model gets multiple attempts. But even with all that, the biggest, baddest models still struggle massively on these deterministic tests. You mentioned ARC-AGI Gemini 2.5 Pro, supposedly state-of-the-art, scores under 5% on the hard part. That's pretty bad.
So if the giants are stumbling, maybe size isn't the answer here. Now, before TRM, you mentioned its predecessor, the Hierarchical Reasoning Model, HRM. That one showed some early promise, right? Small network, recursion. But it sounds like it was maybe overly complicated.
Exactly. HRM was sort of the first step in this direction, around 27 million parameters. Still tiny compared to LMN, but not as tiny as TRM. And yeah, the core argument from the TRM paper is that HRM, while promising, had some, let's call them theoretical imperfections and design complexities. TRM's whole thesis is simplify HRM rigorously, correct its flaws, slash the parameters down to just 7 million, that's less than 0.01% of some big models, and actually get better results, better generalization.
Okay, but hold on. In AI right now, everything's about scaling laws, bigger is better. Isn't that almost counterintuitive to deliberately shrink the model like that? Why not just make HRM bigger if it had issues?
That's the key insight, isn't it? The TRM authors argue the problems weren't about a lack of capacity. There were fundamental issues in the design and the theory HRM was using. So to really appreciate what TRM did, we kind of have to unpack what HRM was trying to do and where it went slightly astray.
All right, let's do it. What was HRM's structure?
Okay, so HRM had basically two main novel ideas. First, this recursive hierarchical reasoning setup. It used two separate small networks. Think of one as maybe a low-level detail tracker and the other as a high-level synthesizer, 5 hours.
And they ran at different frequencies.
Yeah, the paper mentions some biological inspiration for that, though the TRM authors later questioned if that justification was strictly necessary from an engineering perspective. The second novelty was deep supervision.
Deep supervision.
Oh, right.
It's about reusing features.
Exactly. It reused latent features from previous steps, said Mahler's out, and $6 over potentially many steps, up to 16 in their experiments. This gave it an effective depth of something like 384 layers, even though the actual networks were small. Great for getting depth without huge memory costs per layer.
But backpropagating through 384 effective layers sounds computationally intense.
Extremely. And that's where HRM introduced this theoretical shortcut, the thing TRM really takes issue with. It involves something called the implicit function theorem, or IFT.
Ah, okay. The IFT. This sounds like the crucial part. How did they use it?
Well, to save memory during backpropagation, the HRM team made a big assumption. They assumed their recursive function would settle into a fixed point, like an equilibrium state, relatively quickly. Based on that assumption, they used a one-step gradient approximation derived from the IFT. This meant, practically, they only needed to backpropagate gradients through the very last 2 steps of the recursion, even if the forward pass took, say, 6 steps. Big memory saving, potentially.
So it's like trying to speed read a recipe. Skipping ahead, assuming you already know the middle steps, just to get to the end faster.
That's a great way to put it. And the TRM paper basically came along and said, hold on, let's check if the recipe actually works when you skip those steps. They rigorously tested that fixed point assumption. And it turned out the assumption was likely violated. The evidence suggested that when HRM applied this IFT shortcut, The internal state, those latent features, were not actually at equilibrium. The fixed point hadn't been reached.
Ah, so the shortcut wasn't just a shortcut. It was potentially introducing errors into the learning process itself.
Precisely. That theoretical compromise seems to have significantly hampered its ability to learn effectively, especially for generalization. It wasn't just the big model struggling. The first small recursive attempt also had issues, but different ones based on trying to be too clever with the math, maybe.
It really does seem like complexity, whether it's sheer scale or tricky math, can be the enemy for these specific reasoning tasks.
Yeah, and HRM had other practical inefficiencies too. It used this mechanism called adaptive computational time, ACT, to figure out when the recursion should stop, which is a good idea in principle. But the way HRM implemented it required two separate forward passes through the network for each optimization step during training, one to calculate the main loss and another for a continue loss to help ACT learn. That really slowed down training.
Okay, so HRM had promise, but it was complex, theoretically shaky on the IFT part, and inefficient to train. Let's turn the corner. How did the tiny recursive model fix all this?
Right, TRM, step one, radical simplification. They went down to a single network, just 2 layers deep, tiny.
2 layers, wow.
And crucially, they completely ditched the IFT approximation. No more fixed point assumptions, no more one-step gradient shortcuts.
So they just did the full backpropagation.
Yeah.
Through the whole recursion.
Exactly. They decided to just accept the higher memory cost per recursive step and do the full mathematically correct backpropagation through however many steps the recursion took.
But wouldn't that be slow or memory hungry?
Well, because the core network itself was now so incredibly small, just 7 million parameters, they could actually afford it, the memory cost per step was manageable. And the impact? It was massive.
How massive?
Remember that Sudoku extreme benchmark? HRM, with its IFT shortcut, got 56.5% accuracy. TRM, by removing the shortcut and doing proper backpropagation, jumped to 87.4%.
Whoa, that's over a 30-point jump just from fixing the math.
Insane, right? It's probably the single biggest piece of evidence in the paper. It screens that for these hard reasoning problems, theoretical correctness and sound gradients beat parameter count or clever shortcuts, hands down.
Okay, that's huge. What about the 2 latent features? HRM had that complex Philidor and Fither hierarchy based on biology. Did TRM keep that?
Nope, they simplified that too. They stripped away the biological justification and offered a much more straightforward, intuitive explanation.
Which is?
They essentially said, look, you need 2 pieces of information passed along each recursive step. One is the current proposed solution or output, let's call it no, which roughly corresponds to HRM's ZOO or guess.
Okay, the guess.
Right. And the second feature, let's call it roughly HRM ZEAL, is the crucial one. It's the latent reasoning state. Think of it like the model's internal scratch pad or its chain of thought trace.
Ah, so it's tracking how it got to the guess no.
Exactly. It's the model basically talking to itself, keeping track of the reasoning process. If you only pass the proposed answer to the next step, the model might just guess again, forgetting why it made the previous guess. But if you pass both Xiaol and Zellers, the guess and the reasoning trace the model can actually perform iterative self-correction. It can look at its previous reasoning and its previous answer to make a better guess next time.
And they tested this. Does having both really help that much?
Oh, yeah. They ran an ablation study. When they tried using only a single latent feature, just passing dollar essentially, accuracy on Sudoku Extreme plummeted. It went from that 87.4% all the way down to 71.9%.
Wow, so you absolutely need that reasoning trace, that cellular feature, for the recursion to work effectively. It's not just repeating, it's refining.
Precisely. It enables genuine iterative improvement.
Okay, but the most, anti-establishment finding seems to be about the model size itself. 2 layers being optimal, not 4, not more. That just goes against everything we hear about needing deep networks.
It's super interesting, right? And it connects directly to the data scarcity issue. They actually tried a 4-layer TRM. More capacity should be better, right?
Yeah, you'd think.
But generalization got worse. The 4-layer model started overfitting much more easily. Remember, for something like Sudoku Extreme, the training set is tiny e. Maybe only 1,000 examples.
Right, not much data to learn from.
Exactly. So when data is that scarce, having too much model capacity is actually a liability. It just memorizes the training data instead of learning the underlying rules. The 2-layer TRM, combined with the depth provided by recursion, hit this sweet spot. Enough complexity to reason via iteration, but not so much capacity that it overfits the limited data. It's incredibly disciplined design.
That makes sense. Discipline and capacity, discipline in the math.
Yeah.
Did they also improve the training efficiency, that ACT issue from HRM?
They did. They simplified the adaptive computational time mechanism. Remember, HRM needed 2 forward passes because of this extra continue loss.
Yes, slowed things down.
TRM got rid of that continue loss. They simplified ACT down to a single binary cross-entropy loss, just focused on predicting the probability of stopping the recursion at each step. This cut the required forward passes during training in half.
Nice. So faster training and better generalization.
Yep. More efficient all around. Size, training time, performance.
What about self-attention? That's the core building block of most transformers and LLMs. Did TRM use it?
They took a very pragmatic, task-specific approach here. For tasks with small, fixed-size inputs, like the 9x9 Sudoku grid, they found that replacing the self-attention layer with a simple MLP, a standard multi-layer perceptron, actually gave better generalization. That contributed to the 87.4% Sudoku score.
So they did self-attention sometimes.
For those specific tasks, yes. But, and this is important, they didn't just throw it out completely. For tasks with larger or variable input sizes, like bigger 30 by 30 mazes or the visual patterns in ARC-AGI, they found that self-attention was still necessary and beneficial.
So they adapted the architecture based on the problem structure, using MLP for fixed local reasoning, attention for broader context.
Exactly. It shows they weren't just following dogma, but choosing the right tool, the right inductive bias for the specific data structure.
Okay, let's get to the bottom line, the performance results. This tiny 7 million parameter TRM versus the giants on ARC-AGI. Lay it on us.
All right, prepare to be amazed. On ARC-AGI-1, the first part of that challenge, TRM hits 44.6% accuracy.
44.6% with 7 million parameters. How does that compare?
Okay, Deepseek R1, a model with 671 billion parameters, nearly 100,000 times bigger, only scored 15.8% on that same benchmark.
That is staggering. It's not even close.
It's really not. It's like, yeah, bringing a tank to a knife fight and somehow the knife wins. And HRM, the predecessor, it was at 40.3%, so TRM clearly improved on it too.
And the really hard part, ARC-AGI 2, the one where even Gemini struggled.
PRM achieved 7.8% accuracy there. Remember, Gemini 2.5 Pro was at 4.9%. Deepseek R1 was even lower at 1.3%.
So this 7 million parameter model significantly outperforms models orders of magnitude larger on this benchmark known for hard reasoning.
It's a massive statement. It doesn't mean LLMs are useless. Obviously, they do amazing things. But for these specific hard logical reasoning tasks, TRM demonstrates pretty convincingly that brute force scaling isn't the only answer, and maybe not even the best one. Architectural choices, theoretical soundness, and efficient recursion matter immensely.
There was one more detail: stability, especially with small data sets. They mentioned using EM.
Yes, exponential moving average. That's more of a practical training technique.
Yep.
When you have so few training examples, like 1,000, the training process can be unstable. The model's performance can suddenly collapse.
Right.
EMA helps smooth things out. It keeps a moving average of the model's weights during training. It's a technique borrowed from areas like diffusion models, and it just helps prevent those sharp drops in performance and leads to more stable, reliable training, which is crucial when your data is so limited. Just good housekeeping, really.
Okay, so let's try and wrap this up. The big takeaway from this deep dive into TRM seems to be, well, that intelligence, at least for these kinds of logical puzzles, doesn't necessarily need a trillion parameters. It seems to thrive on disciplined recursion, making the right architectural choices, like using that crucial reasoning trace C, and maybe most importantly, getting the underlying mathematical principles right, like ditching that shaky IFT shortcut. Simplicity and correctness beat brute force here.
That sums it up perfectly. It's a win for elegance, efficiency, and theoretical rigor. TRM shows a different path forward, proving that massive scale isn't a prerequisite for cracking these specific hard reasoning problems. It's about the process of iterative self-correction. But, even with TRM's success in simplifying and improving things, it leaves us and leaves you, the listener, with a really fundamental question to chew on.
What's that?
Why does recursion, this process of iterating and self-correcting, using that internal reasoning trace, seem to work so much better for generalization on these puzzles than just building a much deeper, larger network that might have the same total computational depth but does it all in one shot? Is there something inherently more powerful about learning step by step, refining your own path, compared to just trying to compute the whole answer at once? The paper suggests it helps avoid overfitting on small data, which makes sense. But the deeper why this iterative refinement process itself is so effective for logic, that's still a really fascinating open question in AI research. Something to keep in mind as you see new developments. Is the answer always bigger models, or is it sometimes smarter iteration?
Less is more. It's a classic saying, right? But in the world of AI, we're usually told the exact opposite. Bigger is better. More data, more parameters, more power. Well, today we're going to look at some really cool research that completely turns that idea on its head, showing how tiny AI networks can actually outsmart the giants. So let me ask you this, and it's a genuinely baffling question. Why do the world's most powerful AIs, the ones that cost billions to train, why do they struggle with puzzles that are honestly pretty easy for us humans? We're talking about things like Sudoku or logic games. It's a real head-scratcher, and it points to this huge gap in how these massive models actually think. And look, this isn't just a feeling or a one-off thing. The numbers are, well, they're pretty brutal. Even when you use fancy techniques like chain of thought, these giant models, we're talking about things like Gemini 2.5 Pro, they're only getting around 4.9% accuracy on some of these really tough reasoning puzzles. Let that sink in. Not 49%, but less than 5%. That's not just a mistake, that's a complete wipeout. It's basically telling us that just making these models bigger and bigger isn't solving the fundamental problem of reasoning. Okay, so faced with this problem, researchers obviously tried to find a solution. And their first big attempt was, well, it was really innovative, but also really complex. Let's dig into this first try, called the Hierarchical Reasoning Model, or HRM for short. So what was this HRM thing all about? The idea was actually pretty cool, and it was inspired by the human brain. The model used two different neural networks that were supposed to talk to each other. Think of it like a fast-thinking network and a slow-thinking network. Kind of like how our own brains have different systems that work at different speeds. A really novel approach for sure, but as we'll see, it came with a lot of complications. And when I say complicated, I mean it. Just look at the list here. You've got two separate networks running at different speeds. The whole justification was based on these complex arguments about biology. But here's the real kicker. Its entire mathematical proof, the thing that was supposed to guarantee it worked, it relied on something called a fixed point theorem. And the researchers basically said, yeah, this theorem probably doesn't even apply here, so not great. Plus, to train it, you had to do 2 forward passes, which is just clunky and inefficient. So you've got this really complex model built on some pretty shaky ground. All right, so that's where things stood. A complicated model with some big problems. And this is where the story gets really interesting. A new team of researchers looked at all that complexity and asked a brilliant question. What if we do the opposite? What if we start taking things away? And that simple idea led to a massive breakthrough. Enter the Tiny Recursive Model, or TRM. And this right here, the title of their paper, says it all. Less is more, recursive reasoning with tiny networks. It's not just a title, it's a whole new philosophy for tackling this problem. So what does this new model actually look like? Well, take a look at this architecture. It's so much cleaner, right? Forget the two networks and the confusing biological stuff. TRM uses just one single tiny network. The way it works is beautiful in its simplicity. It takes the puzzle, makes an initial guess, and then it goes into this recursive loop. It basically thinks about the problem for a bit, refines its own reasoning, and then uses that improved reasoning to make a better guess. And it can do this over and over again, getting a little bit smarter with each loop. Okay, so we know it's simpler, but how exactly did stripping things away lead to better results? Let's get into the nitty-gritty of TRM's elegant simplifications. First up, the most obvious change, the architecture itself. The old model, HRM, used two networks that added up to 27 million parameters. The new one, TRM, it just uses one single tiny network. We're talking as small as 5 million parameters. That's a huge difference. It's not just about looking cleaner. Being 4 times smaller means it's way cheaper to train and run. You could potentially run this on your phone, not in some giant power-hungry data center. Next, they totally rethought the core logic. HRM was bogged down in these complex, hand-wavy arguments about brain hierarchies. TRM throws all that out and reinterprets the whole process as something we all do every day. It's a simple loop. First, you propose an answer. Then, you think about that answer. You develop your reasoning. And finally, you use that new reasoning to come up with a better answer. It's just a natural, intuitive problem-solving cycle. And remember that shaky mathematical theorem that HRM was leaning on? Well, TRM just sidesteps it completely. Gone. Instead, it uses a much more standard and robust training method. It basically lets the model go through its entire thinking process. And if it gets the final answer wrong, it sends the error signal all the way back through every single step of that recursive loop.
This lets the model learn from its entire chain of thought, not just the final step. It's a way more solid foundation, and it gets rid of a huge point of failure. So let's walk through how this recursive loop works in practice. It's super clean. You start with the question, an initial guess, and this latent reasoning state. Then, for a few steps, all the model does is think. It just recursively updates its reasoning. Once it's done that, say n times, it uses that new, improved reasoning to update its prediction. And it can do this whole thing up to 16 times, refining its answer more and more with each pass. So, to recap, we've got a model that is smaller, simpler, and built on a much more solid foundation. But here's the million-dollar question. Does it actually work better? Well, this is where things get really, really impressive. Before we even look at the results, let's just be crystal clear on the size we're dealing with. 7 million. The TRM model that's about to blow our minds has only 7 million parameters. I mean, that's not just small, it's microscopic compared to the hundreds of billions in models like GPT-4 or Gemini. This is something you could run on your laptop, not a supercomputer. And the results? Honestly, they're kind of shocking. On a really tough Sudoku test, the old, more complex HRM model, the one with 27 million parameters, it got 55% right. Not bad. But the new, tiny 7 million parameter TRM, it scored an incredible 87% accuracy. I mean, think about that. It's 4 times smaller, but its performance just skyrockets. That is a huge leap. And this table just puts the whole thing into crazy perspective. Look at this. A massive model, Deepseek R1, with 671 trillion parameters, gets a big, fat 0% on this test. 0. The old HRM at least got on the board with 55%. And then there's our tiny TRM, with only 5 million parameters, hitting almost 88%. It's not just beating the giants, it's doing something they literally can't do at all. This isn't even the same sport. So for all the researchers and engineers watching, this next part is for you. This is the proof. It's called an ablation study, which is a fancy way of saying they broke the model on purpose to see which parts were most important. And check this out. When they used the flawed training method from the old model, accuracy craters back down to 56%. When they went back to using 2 networks, it was still pretty good, but it dropped to 82%. It's only when you put it all together, the single network and the full proper training, that you get that peak 87% score. This proves that every single one of those simplifications wasn't just for looks. They were absolutely critical to making it work so well. So, what does all of this mean? When you put all this data together, it points to a really powerful conclusion. And maybe, just maybe, a whole new path forward for AI. The big takeaway here is pretty clear. When it comes to hard reasoning tasks, the kind of problems that need step-by-step thinking, brute force isn't always the answer. Just throwing more data and bigger models at the problem doesn't work. What this shows is that a smarter architecture, one that lets a model think, reflect, and refine its own answers, can be way more powerful and a heck of a lot more efficient than a giant model that's just trying to guess the right answer in one go. And that leaves us with a really big, kind of provocative question to end on. We've just seen a tiny, specialized model solve a problem that a massive general-purpose AI is completely blind to. So it has to make you wonder, right? What other huge challenges in science, in engineering, in logic, what other problems are we failing to solve? Not because we need bigger, more powerful AI, but because we've just been using the wrong tool for the job all along. It really seems that sometimes less really is more.